As mathematicians attempted to solve problems using their own individual methods, some of them became popular within the circle of mathematicians, and eventually they had their problems even named after that person. Hi, my name is Tom Atwater, and one of the methods we'll peruse in today's lesson is the Simpson's rule. But let's start by looking at something called the trapezoidal rule. The trapezoidal rule is another method that we can use for finding the area under a curve. We can approximate the integral from a to b of f of x dx and use capital T, standing for the trapezoidal rule, that it's equal to h over 2 times the quantity y sub 0 plus 2 times y sub 1 plus 2 times y sub 2 all the way up through 2 times y sub n minus 1 plus y sub n, where the closed interval a to b is partitioned into n subintervals of equal length, which is h equals b minus a, that quantity, divided by n. Let's try an example of where we use the trapezoidal rule. Use the trapezoidal rule with n equals 4 to approximate the value of the following integral. Use the concavity of the function to predict whether the approximation is an overestimate or an underestimate. Finally, find the integral's exact value to check your answer. And the integral is the integral from 0 to 4 of the square root of x dx. All right, so what we want to do is apply the trapezoidal rule to this particular problem. So one of the things we need to remember is that we have n is equal to 4, and that's important because that's the number of subintervals, and that'll allow us to find h. And then let's actually do that where we can find n. So, I'm sorry, we know that n is 4, so now let's find h. So h is going to be equal to the b minus a, which is 4 minus 0, that's b minus a, all over n, which is 4, and that means that our step is equal to 1. So, to apply the trapezoidal rule then, we're going to say that it's t equals h over 2, and that's 1 for h over 2, and then parentheses, and now y sub 0 is the starting point, and the starting point, of course, is 0. Then we go plus 2 times y sub 1. Y sub 1 is one step up from 0, and one step refers to h, which we know is 1, so it's going to be 2 times 1, plus 2 times 2, because y sub 2 is 1 up from its previous, so it's a step of 1. Then we have to say that we've got the square root of that 2, and then plus we have 2, and again the next step up would be 3 from here, so that would be the square root of 3, and then finally we have plus just y sub 4, which would be the square root of 4. So when we evaluate that whole thing, we will end up with an approximate value of 5.146. Okay, so that's an approximate value because, of course, we have to approximate both the square root of 2 and square root of 3. So now, the next thing we want to do is think about the graph. The graph of this, the square root graph, you should all know by now looks like this, which means that it's concave down, right? Concave down. And so therefore, this is going to be an underestimate. And if it had been obviously concave up, we would be looking at it being an overestimate. The last thing that we want to do, or the final step in this, was to evaluate the integral exactly. So let's take a look at what that would be. So we're going to take the integral from 0 to 4 of the square root of x dx. So to integrate the square root of x, remember that that's the same as x to the 1/2, and that may make it a little bit easier for you to then see that this would be x raised to the 3/2. But then, of course, we need to put a 2/3 out in front so that they would cancel each other out. And that's going to be evaluated from 0 to 4. And when you work that out, I will just tell you that we get 16/3. So that's the exact value that we would be getting by evaluating that integral. So the approximation is fairly good in that this, if we worked out 16/3 versus what we had before, it's a close approximation. Let's look at another approximation method that we have called the Simpson's rule. And the way the Simpson's rule works is this. Again, to approximate the integral evaluated from a to b of f of x dx, use capital S for Simpson's rule, and that's equal to h divided by 3 times the quantity, y sub 0 plus 4 times y sub 1 plus 2 times y sub 2. And now that coefficient alternates back and forth between 4 and 2, 4 and 2, all the way up through 4 times y sub n minus 1 plus y sub n, where the closed interval a to b is partitioned into n subintervals of equal length, where h is equal to b minus a, that quantity, divided by n. Let's do an example of where we apply Simpson's rule. And so let's take a look at using Simpson's rule with n is equal to 4 and approximate the value of the following integral. And then find the integral's exact value so we can check our answer. And the integral that we have is the integral from 0 to 2 of x dx. All right, so the first thing we want to do is set up Simpson's rule. Again, we remember that we have n is equal to 4. And therefore, h is going to be equal to 2, which is b, minus 0, which is a, over 4, which is our n value. And that gives us a step of 1/2. So then, in terms of Simpson's rule, S is going to be equal to, h is 1/2, and then that's over 3. Then we have times y sub naught. In this case, we start at 0 again, and then we take 4, and then the step this time is 0.5. So we go up from 0, so it's just to 0.5. Then we would have plus 2 times 1, because again, the step is 1/2, so from 1/2 plus 1/2 would give me 1, plus 4 times 1.5, and then plus the final step for y sub 4 would be up to 2. Again, when we work all of this out, this actually works out to the number 2. And I'm going to now look at what happens when we evaluate it exactly. In other words, evaluate the integral exactly, and let's see what we come up with. So let me write my answer of 2 up there, because that's what we got when we did it using Simpson's rule. So now let's integrate from 0 to 2 x dx. So that's going to be x squared over 2, and we're going to evaluate that from 0 to 2. And that's going to give us 2 squared over 2. And of course, when you plug 0 in there, that's just going to give us minus 0. And of course, 2 squared is 4. 4 divided by 2 is 2. And in this particular case, Simpson's rule gave us the exact value that we got when we evaluated the integral. All right, well, that's great. Now it's time for you to try a problem. I would like you to use Simpson's rule with n is equal to 4 to approximate the value of the following integral. Then I want you to find the integral's exact value so that you can check your answer. Pause the video while you work on this problem. When you're finished, restart the video to check your solution. Welcome back. Let's find out how you did on this problem. There's our integral from 0 to 4 of the square root of x dx. I've asked you to use Simpson's rule for this with n is equal to 4. So n equals 4. Then we calculate h, and h is equal to b minus a, which in this case is going to be 4 minus 0, and then divided by n, which is 4. So you should have found that the step is equal to 1. Remember that the function that we're evaluating is y equals the square root of x. So when I set up my rule, Simpson's rule, I need to remember that we are plugging in each x value and evaluating the square root of that. So s is going to be equal to h, which we found to be 1, over 3. And then the y sub naught is, we start at 0, plus 4 times y sub 1. Well, first of all, the step we found was 1. So we're going from 0 plus 1 is 1. But then we're taking the square root of 1, which, of course, is just 1. Then we're going to have plus 2 times, well, again, the next step up is 1 plus 1 plus 1 for 2, but then we have to evaluate the square root of 2. So this would be square root 2 plus 4 times, well, it's going to be the square root of 3 because that's the next step up. And then finally, y sub 4 is going to be the square root of 4. So there's the expression that we need to evaluate to come up with the approximation according to Simpson's rule. So when we do that, we'll find that s is going to be equal to approximately 5.2522. And that's the answer we get by using the Simpson's rule. The next step was to evaluate the integral exactly and to check to see how good Simpson's rule has done here. So remembering 5.2522, and I will write that up here again, 5.2522. And now let's do the integral. So the integral is going to be the square root of x dx, and that's evaluated from 0 to 4. And that, remember, we looked earlier at the square root of x, and we found, of course, that it was x to the 1/2, which gives me my 3/2 here, puts my 2/3 out there. And we need to evaluate that from 0 to 4, which we've actually did this earlier. And again, when 0 goes in, we know that that's just going to be 0. So all we're concerned with is the 4. And when you evaluate that, you get 16/3. So again, exactly would be 5.3 repeating. So our approximation is fairly good with respect to the exact value. But now, these are just approximations, which means, as we can see, there's some error involved. And what mathematicians like to do, of course, is evaluate how that error is working. So let's look at the formulas that will help us to calculate the error for both the trapezoidal and Simpson's rules. We refer to these as error bounds. Okay? If capital T and capital S represent the approximations for the trapezoidal rule and the Simpson rule, of course, of the integral evaluated from a to b of f of x dx given by the trapezoidal rule and Simpson's rule, respectively, then the errors E sub capital T and E sub capital S satisfy the following formulas. The absolute value of the error for the trapezoidal rule is going to be less than or equal to b minus a divided by 12 times h squared, and then we have what's called the maximum value of the second derivative. Then, for the error with Simpson's rule, it's the absolute value of E sub s, and that's going to be less than b minus a divided by 180 times h to the fourth power, and this time the maximum value of the fourth derivative. So we know that AB is a closed interval, and it's the integral of integration. H is the same thing, the length of each subinterval. And as I said, m sub f double prime is the maximum value of the absolute value of the second derivative on that interval from A to B. And that m sub f of 4 is equal to, that's here, the maximum value of the absolute value of the fourth derivative on the interval from A to B. Well, you can see that it's possible to calculate the errors, so let's give it a try by looking at an example. Consider the integral from -1 to 1 of sine of x squared dx. Find f double prime, the second derivative, for f of x. Then graph y equals f double prime, the second derivative, in the viewing window, -1, 1 by -3, 3. Then explain why the graph in B suggests that the absolute value of the second derivative is less than or equal to 3 for the interval of x being -1 to 1 inclusive. Then show that the error estimate for the trapezoidal rule in this case becomes the absolute value of E sub t is less than or equal to h squared divided by 2. Then show that the trapezoidal rule error will be less than 0.01, in other words, less than 1/100th, if h is less than 0.1 or 1/10. And finally, how large must n, the number of subintervals, remember, be for h to be less than 0.1 or 1/10? So we have a lot of work to do here. We have 5 different parts, actually 6 different parts that we want to find answers to. So let's get going. We have f of x is equal to sine of x squared, and we want to find the second derivative, which means, of course, we need to do the first derivative first. So the derivative of sine x is cosine x. However, we have to apply the chain rule to this, which would give us an additional, of course, 2x. And now, when we want to find the second derivative of this, we're going to have to use the product rule, which tells us to take the first function, cosine x squared, multiply it times the derivative of the second function, so the derivative of 2x is 2, plus the second function, which is 2x, times the derivative of the first function. The derivative of cosine is negative sine x squared. And then we need to multiply that, of course, using the chain rule, times 2x. When we simplify that as much as possible, we'll get 2 cosine x squared plus, I'm sorry, it's going to be minus, take the minus outside here, and we have this times this for 4x squared times sine x squared. So that's going to be my second derivative. Now, plugging this into the graphing calculator and using the window of -1 to 1 and -3 to 3, we come up with this graph right here. And so the point of it was to show that the absolute value of the second derivative was less than 3. And you'll notice that if we look at these points out here, which is where 1 and -1 are, you can see clearly, since this is my -3, that they are going to be slightly above that. And of course, up here, it's equal to 2. And so we can clearly see that in this particular case, the graph indicates that that value is between, or is less than 3, or the absolute value is less than 3. Okay, the next part was to calculate the error of the trapezoidal rule. And so let's do that next. That's going to be B, which, I'm sorry, B is 1, so I'll just plug it right in now. 1 minus A, which was -1, over 12. Then we have H squared, and then times 3. And when we work all of that out, in terms of canceling, this is 2 here, and that helps to cancel this down to 2. We get H squared over 2. And then what we were asked to do is actually evaluate that when H is equal to 1/10. So we would have E sub t, absolute value, is going to be less than or equal to 0.1 squared over 2. And all that they were really interested in was showing that that was going to be less than 1/10. And of course, 1/10 squared divided by 2 is going to be less than 1/10. The last thing that they asked us to do was to talk about how many subintervals would be necessary in order for the error to be less than the 1/10. And when you calculate that out, that is when you take the same formula where and calculate the answer for n, you will find that n has got to be greater than or equal to 20. So you need 20 subintervals to bring the error down to a more reasonable level. Okay, that was a great lesson. In today's lesson, we looked at being able to approximate integrals using the trapezoidal rule and Simpson's rule. Then we looked at how you could calculate the amount of the error that was involved by using those approximations. Be sure to work the exercises that your teacher assigns, and we'll see you next time.